it has discovered 3 new particles which could help us learn how our universe was born.
This opens a new era of exploration at CERN.
You can think about this a little bit like a time machine.
The universe operates in ways both wondrous and mysterious. As science endeavors to unravel its intricacies, some discoveries transcend our foundational understanding. CERN, the European Organization for Nuclear Research, is at the forefront of such profound revelations. Herein, we dive into 10 of CERN's most shocking findings, each promising to reshape the very fabric of our understanding. Number 1. The mysterious pentaquark particle. A deep dive into the subatomic world often brings to light phenomena that challenge our established knowledge. Such is the story of the pentaquark particle. In the domain of particle physics, quarks are fundamental entities, traditionally combining in sets of 2s or 3s to constitute protons, neutrons, and other particles. However, a discovery at CERN's Large Hadron Collider, LHC, added a remarkable twist to this narrative. In 2015, after meticulous analysis of data from the LHCb experiment, CERN scientists announced the discovery of a new class of composite particles, the pentaquarks. Unlike the familiar baryons and mesons, which consist of 3 and 2 quarks respectively, pentaquarks, as the name suggests, are composed of 5 quarks, specifically 4 quarks and 1 antiquark. The genesis of the pentaquark particle lies in the early 1960s. Theoretical predictions had hinted at the possibility of such a state of matter. Despite numerous attempts to detect them in the decades that followed, experimental evidence remained elusive. Many of the early claims of pentaquark sightings were retracted, culminating in a skepticism regarding their existence. This rendered the LHCb discovery even more electrifying. Several facets make this discovery so riveting. First, it underlines the versatility of the quark model. That quarks can combine in configurations other than the traditionally understood pairs and trios opens the door to a myriad of new possibilities in particle combinations and interactions. It also has potential implications for our understanding of strong nuclear forces, the very forces that bind quarks together in particles. Further studies are ongoing to decipher the exact properties of pentaquarks. Key questions concern their internal structure, their interactions, and their stability. These insights could provide clues about the behavior of quarks under extreme conditions, perhaps mirroring the state of the universe moments after the Big Bang. Additionally, understanding pentaquarks might give hints about neutron stars' interiors, places where bizarre states of matter could exist due to their extreme density. The pentaquark's discovery is not just an addition to the particle zoo. It stands as a testament to the intricate and complex dance of the fundamental building blocks of the universe. Through this revelation, CERN has underscored the sheer depth of mysteries that the cosmos holds, and our perennial journey to understand them. As we progress in this video, one can only marvel at the universe's ability to continuously surprise, challenge, and enlighten us. Number 2. Antimatter's unexpected behavior. Antimatter has always been at the center of both scientific investigation and science fiction fantasies. This mirror image of matter, where particles have opposite charges, holds tantalizing potential. While matter populates our universe, its elusive counterpart, antimatter, has presented one of the biggest mysteries in science. Why, after the Big Bang, did matter dominate, leaving antimatter in a stark minority? CERN, with its unparalleled infrastructure, has delved deep into the realm of antimatter, producing significant quantities of antihydrogen to study its properties. The goal has primarily been to discern any minute difference between hydrogen and antihydrogen. Such distinctions, if present, could provide a clue to the aforementioned cosmic imbalance between matter and antimatter. Yet the most surprising twist came from studies on how antimatter reacts under gravity. The conventional wisdom dictated that antimatter, although opposite in charge, should fall downwards under gravity, similar to regular matter. However, experiments at CERN introduced a tantalizing possibility. What if antimatter behaves differently under gravity's influence? The results, while not conclusive, posed more questions than answers. Initial observations suggested that antihydrogen might either be unaffected by gravity or, more shockingly, be repelled by it, anti-gravity. While this observation was within the margin of experimental error and remains a topic of rigorous exploration, Even the possibility of such a phenomenon has the power to shake the foundational tenets of modern physics. Understanding the true behavior of antimatter under gravity's influence is not just a theoretical curiosity. It has profound implications for cosmology, particle physics, and our comprehension of the universe's evolution. If indeed antimatter exhibits anti-gravitational properties, it could redefine our understanding of galaxies, black holes, and the very structure of the cosmos. The unexpected behavior of antimatter as observed in CERN's experiments also underlines the importance of empirical studies, even in well-established fields. As theoretical predictions and experimental outcomes diverge, we are reminded of the dynamic nature of scientific exploration and the universe's capacity to confound our most sophisticated models. While the mysteries of antimatter remain only partially unraveled, CERN's forays into this enigmatic realm have brought forth surprises and challenges in equal measure. The unexpected behavior of antimatter serves as a reminder of the vast unknowns that await discovery, driving physicists to delve deeper into the fabric of reality, ever hungry for the next revelation. Number 3. Gravitational waves outside predictions. Gravitational waves, once only a theoretical concept envisaged by Albert Einstein in his general theory of relativity, have now become one of the hottest topics in astrophysics and cosmology. These are ripples in space-time, caused by some of the most violent and energetic processes in the universe, such as the collision of black holes or neutron stars. The 2015 announcement by the LIGO collaboration of the first-ever direct detection of gravitational waves was nothing short of revolutionary, confirming Einstein's century-old prediction. However, as is often the case in the realm of science, answers lead to more questions. The LHC at CERN, although primarily a particle accelerator, has implications for our understanding of gravity, especially in contexts where quantum mechanics and general relativity converge. The crux of the anomaly revolved around hypothetical particles and mini black holes. The latter, as the name suggests, are diminutive versions of the colossal cosmic entities known to swallow light. If the energies at the LHC were high enough, and if certain theories of gravity were correct, the collider could produce mini black holes, which, in turn, might emit gravitational waves different from those predicted by Einstein's theory. However, it's crucial to approach these findings with a blend of curiosity and caution. Given the groundbreaking nature of these observations, scientists worldwide have been both excited and skeptical. Some believe that these gravitational wave anomalies might just be ephemeral, vanishing upon more rigorous scrutiny. Others view them as the first cracks in our established understanding of the universe, heralding a new era of physics. Whichever camp one might lean towards, one fact remains undeniable. These observations have rekindled a fervor in the scientific community. Researchers are now more eager than ever to delve into the enigmatic realm of gravitational waves, hoping to either fortify our current understanding or to unearth new paradigms. In the echoing chambers of CERN, where particles dance and collide, we find a microcosm of the universe's vast mysteries. The unexpected observations regarding gravitational waves serve as a testament to the universe's infinite capacity to surprise, challenging us to perpetually reevaluate, learn, and marvel. Number 4. Hints of a new fundamental force. The language of the cosmos is written in the symphony of forces. Our existing understanding of this symphony is orchestrated by 4 maestros: gravity, electromagnetism, and the strong and weak nuclear forces. Each plays a vital role, shaping the myriad phenomena we witness. However, in the subterranean realms of CERN, echoes of a potential new maestro, a 5th fundamental force, have begun to stir, challenging our symphonic understanding of the universe. Amidst the maelstrom of particles accelerated and collided within the Large Hadron Collider, LHC, certain anomalous patterns emerged. Patterns that the current standard model of particle physics struggled to explain. These patterns were born from the decay of certain particles, particularly the B mesons, which, instead of following predicted pathways, seemed to deviate inexplicably. Such deviations hinted at the influence of a force beyond the recognized quartet. This hint, though subtle, carries profound ramifications. Every force in our universe is mediated by a particle. Photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force, and the still theoretical graviton for gravity. If there indeed is a 5th force, then a new particle, an entirely new piece on the cosmic chessboard, must exist. Some have hypothesized the existence of such a particle, provisionally dubbed the X-17 boson, because of its expected properties. Understanding and confirming this force could unlock doors to realms previously thought inaccessible. For instance, the enigmatic dark matter, which has long eluded direct detection, might interact through this newfound force. This means that our detectors, tuned to the frequencies of the known forces, have been deaf to the whispers of dark matter, communicated through this potential new force. Moreover, the discovery of a new force could be the missing jigsaw piece in the quest for a unified theory of everything, harmonizing the seemingly discordant tunes of quantum mechanics and general relativity. Such a theory has been the holy grail of physics, offering a comprehensive description of the universe's workings, from the tiniest particles to the vastest galaxies. However, the path to discovery is strewn with cautionary tales. Science has often been teased with initial hints of groundbreaking discoveries, only for subsequent experiments to attribute anomalies to statistical fluctuations or overlooked external factors. Hence, while the excitement within the scientific community is palpable, there remains a consensus on the need for rigorous validation. Independent experiments, peer reviews, and repeated tests are crucial to move from hints to confirmation. As CERN delves deeper, attempting to either solidify or refute these hints, the world watches with bated breath. The possibility of a new fundamental force underscores the fluid, ever-evolving nature of scientific understanding. It's a reminder that the universe, in all its vastness, still holds secrets, waiting for the curious and the tenacious to unearth. Whether this hint culminates in a paradigm-shifting discovery or merely adds to the tapestry of scientific exploration, it serves as a testament to humanity's insatiable quest to understand the cosmos's symphony. Number 5. Unveiling the secrets of the Higgs boson. The discovery of the Higgs boson in 2012 at CERN's Large Hadron Collider, LHC, was a watershed moment in particle physics. Often dubbed the God particle in popular media, its detection was the crowning confirmation of the Standard Model, validating decades of theoretical work. But, as with all significant breakthroughs, the discovery of the Higgs was not an endpoint, but a thrilling new beginning, opening doors to deeper mysteries and challenges. The significance of the Higgs boson lies in its role in the Higgs field. This omnipresent field is thought to give particles their mass by interacting with them. The more a particle interacts with the Higgs field, the heavier it becomes, and vice versa. The Higgs boson is the manifestation of excitations in this field, a glimpse into the very mechanism that endows particles with mass. Moreover, there was the question of the Higgs field's stability. Given the observed mass of the Higgs boson, the universe seems to be in a delicate balance, described by some physicists as being in a metastable state. This means that a significant disturbance could, in theory, destabilize the Higgs field, leading to catastrophic consequences for the universe. Such considerations bridge the gap between particle physics and cosmology, tying the fate of tiny particles to the destiny of the universe itself. CERN's continued investigations into the Higgs boson have also sparked discussions about potential connections to dark matter. Some theories suggest that the Higgs might decay into dark matter particles under certain conditions. While no conclusive evidence has been found, the mere possibility has reinvigorated efforts to detect and understand the universe's elusive dark components. The Higgs boson, while a remarkable discovery, remains a font of enigmas. The intricate dance of its properties, its influence, and its connections to deeper cosmic mysteries ensures that it will remain at the forefront of particle physics research for years to come. CERN's explorations into the Higgs underscore the iterative nature of scientific discovery. Every answer births new questions, driving humanity's relentless pursuit of understanding in the vast cosmic arena. Number 6. Neutrinos oscillating between forms. In the subatomic realm, where particles flirt with the bounds of understanding, neutrinos are particularly enigmatic dancers. These ghostly particles, billions of which pass through us every second, have always intrigued scientists due to their elusive nature. But CERN's revelations about neutrinos oscillating between different forms, or flavors, added another layer of mystery to these already puzzling entities. The evidence for oscillation first came from solar neutrinos, those emanating from the sun. Experiments detected fewer electron neutrinos arriving on Earth than predicted, leading to the solar neutrino problem. The solution to this puzzle lay in the realization that these neutrinos were not disappearing, but changing flavors during their journey from the sun to our detectors. CERN's contribution to this field has been immense. The laboratory's experiments further scrutinized the oscillation phenomenon, delving deeper into the conditions and parameters governing these transitions. One such experiment, T2K, sent a beam of neutrinos over long distances to observe their flavor transitions. The results not only confirmed the oscillation phenomenon, but also shed light on the differences in behavior between neutrinos and their antiparticle counterparts, antineutrinos. Understanding neutrino oscillations is paramount for multiple reasons. Firstly, it provides crucial insights into the fundamental properties of neutrinos, such as their masses and the way they mix. These parameters are essential components of the standard model of particle physics, and any deviation from predictions could hint at new physics beyond the model. Secondly, neutrinos play a pivotal role in cosmological events, from the dynamics of supernovae to the early processes following the Big Bang. Grasping their oscillation patterns allows for a clearer picture of the universe's evolution and the processes molding its structure. Lastly, the very existence of neutrino oscillations touches upon profound questions about the universe's matter-antimatter asymmetry. Why is there more matter than antimatter? Do neutrinos and antineutrinos oscillate differently, contributing to this imbalance? These are questions at the heart of understanding our universe's very existence. CERN's research on neutrino oscillations epitomizes the essence of frontier science. It showcases the journey from perplexing observations through rigorous experimentation and analysis to groundbreaking discoveries that reshape our comprehension of the universe. The oscillating dance of neutrinos, shifting between forms as they traverse space, serves as a poignant reminder. The universe, in all its vastness, is replete with intricate details, waiting for the discerning eye of curiosity to unveil and understand. Number 7. The quark-gluon plasma revelation. Peering into the heart of matter often leads us on a journey back in time, to the earliest moments of our universe. In the high-energy environment of CERN's Large Hadron Collider, LHC, researchers have replicated conditions not seen since microseconds after the Big Bang. Their objective? To witness the quark-gluon plasma, a primordial state of matter where protons and neutrons melt into a soup of quarks and gluons. Quarks and gluons are fundamental components of protons and neutrons, the building blocks of atomic nuclei. In our current universe, under normal conditions, quarks are never found alone. They're always bound together by gluons, forming protons, neutrons, and other particles. This binding phenomenon is governed by the strong nuclear force, one of the 4 fundamental forces of nature. However, as scientists hypothesized, there was a time in the early universe when energies were so high that quarks and gluons existed freely in a hot, dense state, the quark-gluon plasma, QGP. This state would have persisted until the universe cooled and quarks bound together to form the particles we recognize today. CERN's ALICE, a large ion collider experiment, was designed to explore this very state. By colliding heavy ions like lead at near light speed, temperatures and densities were achieved that mirrored those of the universe's infancy. The aftermath of these collisions allowed researchers to study the properties of the QGP, drawing conclusions about its behavior, viscosity, and other characteristics. The revelations were profound. The QGP was not a gas-like state as some had anticipated. It behaved more like a liquid, albeit one with incredibly low viscosity. This perfect liquid nature of the QGP was a significant discovery, challenging previous notions and leading to new questions about the early universe's behavior. Moreover, the study of QGP provided a deeper understanding of the strong force. By observing how quarks and gluons interact in this primordial soup, researchers could probe the nuances of this fundamental force at energies and conditions not achievable otherwise. CERN's foray into the realm of quark-gluon plasma stands as a testament to humanity's drive to understand the universe's origins. By recreating and studying this fleeting primordial state of matter, scientists have not only glimpsed the raw fabric of the cosmos, but also deepened our understanding of the intricate tapestry woven from quarks, gluons, and the forces that bind them. Number 8. B mesons defying the Standard Model. The vast framework of the Standard Model in particle physics has proven its mettle time and again, predicting particle behaviors with remarkable precision. But like all great scientific theories, its true strength lies in its adaptability to unexpected findings. One such curveball has been thrown by the B-mesons, particles that have shown hints of behavior that deviates from what the Standard Model anticipates. B-mesons are composite particles containing a bottom quark bound to another type of quark. Given their composition and properties, their decay patterns and processes have been well charted within the Standard Model's predictions. However, experiments at CERN's LHC began to reveal anomalies. The LHCb, Large Hadron Collider Beauty experiment, specifically designed to investigate the properties of particles containing bottom quarks, reported unexpected results when studying certain decay channels of the B-mesons. Instead of decaying into products at the rates the Standard Model predicted, B-mesons showed a preference for certain pathways more than others, leading to an excess of some particles and a dearth of others. This deviation, though seemingly minor, has profound implications. If confirmed with higher precision, these findings suggest the presence of forces or particles not accounted for in the Standard Model. Potential candidates could include virtual particles that momentarily come into existence, influence the decay process, and then vanish. Such virtual particles could belong to a family of yet undiscovered heavier particles that lie beyond our current understanding. The stakes are high in the world of particle physics. If B-mesons truly defy the predictions of the Standard Model, it could be the first step towards a new era in our understanding of the universe. A new, more encompassing theory might be required, potentially unveiling hidden sectors of the universe filled with unknown particles and forces. However, caution is the watchword. The history of physics is littered with tantalizing hints that eventually dissolved under scrutiny. Thus, while the findings are exciting, they require rigorous verification, with researchers worldwide striving to either corroborate or refute the LHCb's observations. The B-meson anomalies stand as a testament to the ever-evolving landscape of particle physics. They embody the spirit of scientific inquiry, where every observation, especially the unexpected ones, propels us further in our quest to decode the universe's intricate mosaic. Whether these deviations lead to a paradigm shift or become footnotes in the annals of research, they exemplify the unpredictable and thrilling journey of discovery. Number 9. Discovery of tetraquarks. In the intricate realm of subatomic particles, quarks are foundational. Typically clustering in groups of 2 or 3, they form the familiar protons and neutrons that build atomic nuclei. However, the universe, ever full of surprises, presented physicists with an intriguing puzzle: the tetraquark, an exotic state where 4 quarks are bound together. CERN's Large Hadron Collider, LHC, has been instrumental in exploring the frontiers of our quark knowledge. Traditionally, quarks are understood to combine in 2 principal configurations: baryons, comprising 3 quarks like protons and neutrons, and mesons, made up of a quark and an antiquark. Tetraquarks challenge this understanding, suggesting a more complex quark-binding possibility than previously acknowledged. The discovery journey began with anomalous signals in particle detectors. Researchers noted unexpected bumps or peaks in their data, which didn't fit with any known particles. After meticulous verification to rule out statistical fluctuations or instrumental errors, it became clear that these signals were indicative of new particle states. Deeper analyses hinted at the presence of a 4-quark-bound state, ushering in the era of the tetraquark. The implications of tetraquark discovery are profound. Firstly, it provides a deeper insight into the strong force, the fundamental interaction responsible for binding quarks together. The existence of tetraquarks suggests that this force can facilitate more intricate binding arrangements than initially believed. It also introduces questions about the nature of these bonds. Are tetraquarks truly a quartet of quarks bound together, or are they more akin to a pair of mesons weakly bound in a molecule-like formation? Furthermore, the tetraquark's discovery opens the door to the potential existence of other exotic multi-quark states. If 4 quarks can bind together, what about 5, 6, or even more? This line of inquiry has led to the theoretical proposition and subsequent search for pentaquarks, 5-quark particles, and hexaquarks. In addition to reshaping our understanding of quark dynamics, tetraquarks also have implications for understanding the early universe. The high-energy conditions shortly after the Big Bang might have been conducive to the formation of such exotic states. Thus, tetraquarks could offer a glimpse into the primordial particle soup from which our current universe emerged. The discovery of tetraquarks at CERN's LHC serves as a compelling reminder of the richness and complexity of the subatomic world. Even as the Standard Model stands as a robust framework for understanding particle physics, nature continues to throw curveballs, challenging researchers to expand the boundaries of knowledge. Tetraquarks, with their enigmatic structure and intriguing implications, exemplify the wonder and boundless potential of the quantum realm, ensuring that our voyage into the heart of matter remains a perpetually fascinating endeavor. Number 10. Challenging dark matter theories. The cosmos contains vast mysteries, many of which stretch our understanding to its limits. Among these enigmas, dark matter stands out, an invisible substance thought to compose approximately 27% of the universe's total mass and energy. While its gravitational effects on galaxies and galaxy clusters are evident, its exact nature remains elusive. The experiments and observations at CERN have significantly influenced the conversation about dark matter, challenging and refining existing theories. Yet despite numerous high-energy collisions, WIMPs remain undetected at the LHC, leading to profound implications. The absence of detection has begun to challenge the prevailing WIMP paradigm. This non-observation has led researchers to consider alternative dark matter candidates and theories. One such alternative is the axion, an incredibly light and weakly interacting particle. Unlike the more massive WIMPs, axions would be produced in vast numbers but would require specialized detectors to identify their exceedingly faint signals. CERN has initiated projects like the Axion Solar Telescope, CAST, specifically designed to hunt for these elusive candidates. Another influential CERN experiment is the Alpha Magnetic Spectrometer, AMS, aboard the International Space Station. While not strictly a dark matter detector, the AMS analyzes cosmic rays, high-energy particles traveling through space. Some observed patterns in cosmic rays might result from dark matter particles annihilating or decaying. While the AMS has seen intriguing excesses in certain cosmic ray particles, it's still an ongoing debate whether these signals are genuinely from dark matter or have more mundane astrophysical origins. CERN's research has been pivotal in both narrowing the search and broadening the horizon for understanding dark matter. The non-detection of certain particle candidates has led to tighter constraints on their properties, refining the range where future experiments should look. At the same time, by opening doors to alternative candidates and theories, CERN has ensured that the quest for dark matter remains multifaceted and vibrant. As we peer into the cosmic shadows in our quest to unveil dark matter's true nature, CERN stands as a beacon, guiding, challenging, and reshaping our understanding. The journey underscores a fundamental truth in science. In the interplay between the known and the unknown, every revelation brings new questions, ensuring that our cosmic voyage is ever evolving and endlessly captivating.